going to do today is we're going to develop what are called sum and difference formulas, and we'll get to that in a couple minutes. And in the first segment, what I want to start with is I want to do one more identity with you. Again, it's practicing your algebra skills to learn how to use your trigonometry and algebra to be able to simplify fairly messy expressions. And so I want to do one more of those with you, sort of wrapping up the previous session's identity discussion. And then I want to introduce to you and show you how to remember these sum and difference formulas. I'd like you to commit them to memory because they get used quite a bit. And they're not too hard to remember. It's just a simple, relatively simple pattern. And then in the next segment, the last segment today, what we'll do is we'll actually practice some problems using those formulas. Okay, so let's jump right into it. And what we're going to do is start off with something where there's an algebra structure in this left side on this identity of this trigonometric expression here. There's an algebra structure in here that I want to refresh your memory on. And then over on the right side, that's kind of messy as well. And what do we first of all do when we want to verify an identity?
Draw the line down.
Great. Like Brooke said, you put a line down here so it keeps you from wanting to move things back and forth like you would do solving an equation. Okay? So what we do is we try to adjust each side separately and confirm that one side is identical to the other side. So what I want to review with you real quickly is sums and differences of cubes. If you move the camera a little bit. Gracias. A little more. There we go. Okay. So if you ever see a sum of cubes like you see in this problem right here, we have a sine cubed and a cosine cubed added together, then what you want to always remember is these basic algebra factoring techniques. Most people have trouble remembering this. Here's the world's best way to remember this. If you identify first that you have a sum or difference of cubes, then the first part of the factoring process is easy to remember. It's going to be whatever you see as the basis over here, a plus b or a minus b down here. Now, the hard part for people typically to remember is what goes over here. It's easy. Square the first item you see here where my finger is. Take the product in this binomial, which is AB, and change the sign of it and put it in there, and then square the last item, if you can see that. Okay? So you end up with a binomial and a trinomial. The second one here is usually quadratic in character. Same pattern here. A minus b, square the first, take the product in the binomial minus AB, change the sign of it, put it right there, and then square the last item, which becomes positive b squared. And then don't forget the basic Pythagorean identity down here, sine squared plus cos squared equals 1. With that in mind then, you can come over here and you can take this numerator right here, and instead of, to save space, what I'm going to do is right up above here, I'm going to write the factored form of this sum of cubes. So you're going to see what showing up for factoring the numerator.
Sine theta plus cosine theta.
Okay, hold it. Let somebody else now have some fun here. Okay, somebody near the back of the room.
Sine squared.
Square the first term.
And then
Minus the product sine cosine, right?
Yes.
Minus the sine theta cosine theta. And you don't always want to have this stuff written down. You want to try to get this into your head. Need some more space. And then square the last item of the binomial, so plus cosine squared theta. Feels good. Everybody got it? Okay, so this numerator factors like that. Now, do you see anything over here that might be simple? What do you see, Elizabeth?
Well, the two things you're pointing your little fingers at.
Yeah, that's good.
Don't they also equal 1?
Yes, they equal 1, don't they? We have the sum of sine squared and cosine squared, and that sum is equal to 1. When you see those things, you know, we're trying to help you see these patterns. If you see that, go ahead and replace that with a 1. So let's see what we have. we have sine theta plus cosine theta times 1 minus sine theta cos theta in our numerator. And our denominator is this strange looking thing. This cannot be factored in the algebra structure. You agree? Okay. However, what does cosine squared equal? Look over here. Camera up. Thank you. Cosine squared equals 1 minus sine squared, right? So, I wonder if that would be useful. If we had cosine squared equals, replaced it with 1 minus sine squared in here. Maybe we should try that and see what happens. Be aware that there's a minus 2, right, in front of that. So this denominator then, I'm going to just see what happens. We're experimenting. We're seeing where this takes us, but we don't want to violate any algebra rules. So the denominator is 1 minus twice, and I'm going to replace that with 1 minus sine squared theta. What's that denominator equal to? Doesn't look like it's cleaning up much, does it? Doesn't look like it's cleaning up much. It turns into 1 minus 2, which turns into negative 1 plus 2 sine squared theta. So that looks as bad as what we had up in the original, doesn't it? Right? Okay. So I'm a little stuck right there. So let's go over and play with the other side. All right? We're just playing around. This is the hair pulling I was talking about. Okay? Now, as I said in the previous session, you can always take any trig expression and you can rewrite it in terms of sine or cosine. So this secant we could think of as 1 over cosine, and minus a sine theta, think of that as over 1, and then down underneath our tangent we know of theta is equivalent to sine theta over cosine theta minus 1, and think of that as 1 over 1. So this mess right here we call a what kind of fraction? Complex fraction. The world's best way to clean this up is to take the entire numerator, and I'm repeating myself from the previous sessions, and do what? Multiply the numerator and denominator by the common denominator of all those fractions, which is cosine theta. Right? So we're really multiplying by 1 effectively. And now we distribute. Don't forget the distribution process there. And so we get 1 minus sine theta cos theta in our numerator, and down below we get sine theta minus cos theta. So, what do you think? How close are we? You look at the left side here and the right side, we have this factor in our numerators on the left and the right, don't we? So that's looking pretty good. And what we're trying to do is to get this other part here cleaned up to create that denominator, aren't we? Does anybody see anything we could do here that might be helpful? 1 minus sine theta cos theta. There's our numerator. we transform the denominator into this, but that didn't seem to really help much.
I mean, if you put denominator and numerator, you have to make the
You mean,
negative.
when you say flip, what do you mean?
One on top and
Yeah, if you take something from below and you move it across a fraction bar, you have to change the sign of the exponent. You don't change the sign of the expression, which I think is what you were thinking of.
I was just thinking of all sorts of
Okay, there's multiple possibilities. So I'm kind of puzzled. Did I write this problem down correctly? That's always a good thing to check. It's right. Okay, I wrote it down just the way it's in the book. And so we have this, which I transformed into that, which doesn't look any better. I have a thought. Watch this. Let's see. Let me erase this denominator and leave it the way it was originally. Okay? The numerator we factored and cleaned it up a little bit. In our denominator, we have a 1 minus 2 cosine squared theta. Right there. Now, what I'm toying with is the idea of multiplying, go back over to this side, and multiply this denominator by sine plus cosine. Sine plus cosine. I'd have to do that top and bottom, though. So it's a fishing expedition we're on here, trying to see if we can do something to clean this up. I could multiply this side by what? Instead of multiplying that side by sine plus cosine, top and bottom. What could I do here instead? What do you think? To try something similar, multiply by sine minus cosine, top and bottom, sine minus cosine. And the algebra over here on the recall, let's kick the camera over. The algebra I'm thinking of is this. I can form a difference of squares by taking a sum of terms and multiplying it by the difference of the terms, or vice versa, right? I can form a difference of squares. And I was wondering if that might be a little bit helpful. Oh, I'm seeing something else up here that might be interesting. Right here. There's this 2 here. Now we look at the algebra of this, and I was stuck. I was looking at the algebra of this, and I know this isn't factorable, right? Everybody agree? 1 minus 2, say x squared, is not factorable. Okay? So here's something I want us to think of, though, instead. I think this might be a better way than what I was trying to get at just a moment ago. Why not think of this as 1 minus cos squared theta minus another cos squared theta? Tricky, right? Getting excited now. Why am I excited? Because this little thing right here is sine squared, is it not? 1 minus cos squared is sine squared. So that becomes sine squared theta minus cos squared theta. So then the big mess here is sine theta plus cosine theta times this 1 minus sine theta cos theta all over sine squared minus cos squared, which, as you mentioned, is a difference of squares. It's sine theta plus cos theta times sine theta minus cos theta. And common multipliers in the numerator and denominator, these common factors now of the sum of the terms, sine and cosine, reduce out. And we've got the right side. We are happy. Still have our hair. Okay. I had not done this problem ahead of time, and you saw that I got stuck. That's going to happen to you too. Okay? And so what you do is you back up and you take a relook at the algebra structure and you see if there's another way of tracking your way into it. Okay? All right. Any questions on the algebra in here? Everybody with me? Okay, good. So that's the end of what I want to do with identities. Again, the whole intention of this stuff in trigonometry is to get you so that you can see the algebra structure and simplify expressions that might come at you. And you can see that this final expression we ended up with here is simpler in structure to the originals that you saw up above. And where we're going with this is to help you learn to be able to solve equations, trigonometric equations. Okay. Let's shift gears now and give you a brief introduction to sum and difference formulas. And I think I'll go over on this other board to do that. Here's what's going on when we speak of something called a sum formula. What if I add something to an angle theta? Let's say I add pi over 2 to theta. And I want to figure out the sine of that new angle, theta plus pi over 2. Now what I want to show you is a real handy thing. I've never seen it in textbooks, but it's very useful. If you are ever adding or subtracting, listen to this, if you're ever adding or subtracting a multiple of pi over 2, adding or subtracting a multiple of pi over 2 to an angle theta, and you're looking for one of the trig ratios. Here's what's going on your unit circle. Watch this. Pick some dummy angle, some little simple angle called theta on your unit circle. And you know that that's the sine of theta and that's the cosine of theta. And there's your angle theta. Right? If I add pi over 2 to it, isn't that going to put the terminal side up here? Like that? Right here? At this location? Right?
Yep.
Look at the triangle. This height right here is now the sine of what angle? Theta plus pi over 2. And this little distance, this negative distance you see right there, is the cosine of theta plus pi over 2. Aren't those triangles identical in shape? Aren't they identical in shape? And so if you see the sine of theta plus pi over 2 on this picture, you can look right here, and that's positive, as shown. And that exactly matches, as Diana mentioned, the cosine theta value, equal to cosine of theta. So this thing simplifies to cosine theta. Done. Okay. We've added one multiple of pi over 2. Okay. Watch this. Let's have you do the following. The cosine of theta minus 3 pi over 2. Use the method I just showed. Draw a sketch with a dummy angle theta, where there's your sine of theta and your cos of theta, and then change this, here's your theta, subtract off 3 pi over 2, draw the appropriate triangle, and identify what you could replace this with. Time's up. It's like a game show, right? Wonder how popular this kind of game show would be. Think there'd be a wide audience watching it? Okay, no? Okay, so here's theta. If we back off 3 pi over 2, we're going back 3/4 of a revolution, aren't we? And hey, we're ending up exactly where we were a moment ago. Okay, and so now this is your sine of theta minus 3 pi over 2, that height. And that leg right down there is your cosine of your theta minus 3 pi over 2, right? Look at the triangles, they're identical. So this cosine reading here that you see is negative, it matches what?
The sine.
Careful, not just the sine. This is negative.
Right.
What do you do to that?
Make it negative.
What do you do to that sine? This is the value we're trying to replace right here. What do you replace this with? Don't you take the negative of that value? Isn't that the negative of that?
Yes.
There's the answer right there. Okay. Did you see it or not? Didn't see it. Jason? No, I'm Tom. Yeah, Tom. Didn't see it?
I see how you get the triangle, I just don't.
Okay, do you agree?
Lost it there.
Well, and you're not alone. Half the class is stuck on this. That's why I'm pausing here. Everybody, I think, agrees that this triangle is the same as that triangle. Feel good? Okay. However, when you're sitting here in the second quadrant, this point right here has a y value that's positive, and this x value here of that point is negative. I'm trying to replace this cosine reading, which is that negative reading right there, isn't it? Well, I look over here at this triangle. This length right here is the same as that length, but this value right there is the opposite sign of this thing, isn't it? This is negative, that's positive. If I want to figure out a replacement for this thing, then I better take the negative of that value. Boom, done. It's a geometry thing, but there's plus and minuses associated with the legs. Okay. Now, I'm not going to prove these formulas for you, the general formulas. So you can do, whenever you see multiples of pi over 2 added or subtracted to an angle, and any of the trig ratios, it could be any 6 of them, you can use this little technique to do it without using the fancy formulas that I'm going to show you right now. Okay. I want to first of all mention how you prove these formulas. Here's what we want to try to do. If we have the sine of an angle, let's say alpha, plus another angle, say beta. Then what we'd be interested in doing, if I was going to do the proof of this, and almost all trig books have this in it, if you take and draw a picture of alpha, here's alpha, and you add to it some angle beta, and so let me say beta starts here then and continues on, say, over to here. Now, let me think, hold it, how do I want to do this? I think what I want to do, I'm going to change that. I think I want to be, I believe I was looking in our textbook, and I believe I want to be consistent with what the textbook did, even though textbooks aren't identical, all books. Let's call this alpha, that big angle alpha, that whole thing, all the way over to here. And let's call this angle beta right in there. And what I'm interested in is the sign of the difference between alpha and beta. Alpha and beta. So I'm trying to find the sine of, I have to get the difference of this angle first, and then I need to figure out the sine of that resulting angle. And that angle is sitting right here, isn't it? Isn't this the angle, alpha minus beta, right there? Okay. Now, what we do is we take this point, which has coordinates of cosine alpha on our unit circle, sine alpha, and coordinates of this point right over here, which has coordinates cosine beta, sine beta. And we, in the proof, we write an expression for this distance, that distance between those 2 points. There's a rise between them, and there's a run between them, back at the beginning of college algebra. Okay? Then what we do is we take that unit circle and we rotate it back, so we lay beta, we lay the terminal side of beta right down here, and then the angle alpha minus beta is probably going to be something about like I'm showing here. So we lay this point out here, which is at 1, 0. All I did is I just took this thing, this wedge here, and I rotated it back. Okay? Rotated it back so it sits here. And now we look at the coordinates here, and the cosine of alpha minus beta is the x-coordinate here, and the y-coordinate here on our unit circle is the sine of alpha minus beta. And we write, isn't this distance right here the same as what I've darkened up here? So what we do is we set those distances equal to each other, and we play around in the algebra with those messy trig expressions. Clean them up, and we end up with the following formulas. The sine of alpha minus beta, and it's not too hard to memorize it, is you take the sine of the first angle times the cosine of the other angle, and then use the same plus or minus character here, and then multiply by or subtract from it the opposite combination, the cosine of the first times the sine of the second. That's a formula. It's called a difference formula. Not too hard to memorize. So the sine of a difference of angles is equal to the sine of the first times the cosine of the second. Track the same plus or minus character here, times the opposite combination then, the cosine of the first times the sine of the second. If the two angles are added together, all you have to do is plop a plus sign in right there. Okay. Not too hard to memorize. That's your sum and difference formula for sine. If you have the cosine of the sum or difference, the proof is the same process as I described earlier, where you'd be solving for the cosine of the difference or the sum of the angles. The method of the proof is the same, and you can look it up in a textbook. The way you memorize the cosine formula is it starts with the products of the cosines. The products of the cosines. So the cosine of the first, cosine alpha, times the cosine of the second. And now you switch the plus or minus character on this formula. This becomes then a minus or a plus, the product of the sines. Sine of alpha, sine of beta. And I don't have a very good memory. If I can memorize these things, I hope you folks can, because your memory might be better than mine. Okay. with that, let's end this session, and then we'll start practicing, or this segment, and then in the next segment here on the same DVD, we'll practice using the sum and difference formulas. Okay?